Chris, can you share? Chris, can you share now? Test.
I can hear you, AC.
Okay. I can't hear Chris though. Chris. We got quite a few people.
Mic check 1, 2, 3.
You're good, Tony.
Hey everyone, I see you already counted to 3.
Yeah. Everybody should note to sign the blue sheet.
This is really frustrating.
Can you share now if you
I cannot share. I can't share. I can't share. I can't join as a different user. 10 minutes is not an acceptable preparation time. Like I don't can well, this is probably not the forum, but
yeah.
we need more ability to join earlier than 10 minutes before the meeting. I'm sorry for everyone that we weren't able to join earlier and get this.
Okay, I'm just going to put the note well up then.
The menu item even says anyone can share. It's like
Right.
checked. And then I go change the role and it's ghosted out. It says I'm the presenter. I mean, we're logged in as 2 different people. So I guess we're logged in twice, right? And
Yeah, but I actually closed the meeting.
yeah, I know, I did too. I know what it is. It's because you're from Cisco.
Oh yeah, yeah.
So it's saying, oh,
WebEx country, of course.
if we have 2 from the same account, we're going to prefer the one coming from Cisco.
Yeah.
Okay, anyway, it looks like we were gonna hi folks. So we were trying to swap the duties, and I would share slides and AC would do mic cue. But we're okay. I got Siri talking to me. That's good. But we weren't able to do that.
Okay, I put up the note well. Can everybody see it?
Yeah, I can.
Well, you flipped away from it. It was there for a moment.
Oh, I know what happened. Tony, I let Tony shoot. What happened here? I should know it. Okay, it went back. Okay, good.
We're so screwed. I just said make me the presenter, and it gave it back to you.
Here's the note well. Everybody, first of all, this is the LSR interim, the second of 2, replacing the meetings as part of the IETF 107 LSR meetings. Here's the note, Will. Keep in mind that if you are aware of any IPR, you're obligated to disclose it. You're also, there's also a number of other internet, by participating, agreeing to adhere to another other group of vendors, all these BCPs. The work anti-harassment, code of conduct, copyright, of course, the one we covered, patents. Okay.
So I'm in Jabber. Joel's reminding me to remind people to sign the blue sheets. Thank you, Joel. Can people hear me? Uh-oh.
Yeah, I hear you.
Oh,
I don't
okay.
know about people, but I can hear you.
Okay, good. Thank you.
Since Chris was, I was not going to. I do not have the presentations, but I will have them quickly. Should I have this one? Gives them funny names too. Okay.
I have a button. If I click directly on me, it says become presenter. I can try again.
Um, you can. Okay, go ahead and try.
It says I'm the presenter. Yeah, it still has a ghosted share content.
You can't go to the top and you can't share, huh?
Yeah, I'm looking at WebEx meetings file, edit, share. When I get to share content, share web browser are both ghosted out. Share multimedia is not.
Okay, well, I can share this. Okay, finally we get started. I'm gonna do a brief working group status, and Chris will chime in as well. We've had a lot of this, despite not meeting in person, we've had a lot of progress since Singapore in a lot of areas, and more discussion than usual. That's been good. This is a record on the number of RFCs we published between IETFs. Now, part of it because we had all these MPLS segment routing drafts that were waiting on a final reference. I forget which one it was, but it was a chain of dependencies. So we published those four. We published this long time one, Elbar, Antone and Michael Barnes, Antone Smirnoff, Michael Barnes draft on the cross address family traffic tunnels, and ISI restart signaling. And between the two meetings, the host bit draft published as well. That's good. Hopefully we'll have some before the Madrid replacement interims. We still have the tunnel end cap that is coming. I know that's moving along in IDR, and the 2 Yang models are still waiting on references, the 2 main Yang models. These drafts have basically had a lot of good discussion with Alvaro on updates on the OSPF one. Again, the ISIS is pretty much done. We're still some of the reviews are trickling in from the directorates. So once the ISIS is done, I think it's pretty much done. The OSPF draft will have the similar changes that are analogous. And this one's waiting on Alvaro, the ISIS invalid TLV handling. A good maintenance draft there that was pretty much unanimous consensus on that. This draft, we've had some progress since the last interim meeting, but not enough. It was submitted to the ESG for publication. What I didn't put on here, there's a what do you call that? An appeal on this draft, and there was been made on the SID structure, and we've also got some of the implementers, other than the authors, have come forward and said that okay, this is okay. So we have had some progress, but I think not enough. I'm going to let Chris talk about it since he's the shepherd on this one.
Yeah. So I mean, there's a lot of contention on the base network programming draft. Well, I don't know how much contention, but it's in appeal. If you followed the list in the spring, or maybe it's been CC'd in. No, I don't think so. Anyway, there's an appeal filed about the penultimate hop. There's other aspects to the appeal. Anyway, it's a lot of raging anger maybe that we don't want to touch. I think that the draft as it is, I mean, it's whether we need to make small changes, I don't think there's any reason to bring that contention to us. So, we have something that's sort of ready to go to support the network programming document. But we're going to hold back on actually submitting this to the IESG, primarily to avoid, taking on that poison pill. We could become a part of the appeal then, because it's sort of, an end run around the process if we're pushing through extensions to support something that hasn't been standardized that's under appeal. That said, we can get up to the point where, I mean, I think we're kind of at the point, right? There was the debate on the SID structure, but I think that whatever the network programming draft describes is what we should support. I don't think, unless people disagree with that, I mean, that seems logical. So I think that we should just wait and see how this plays out. And then once the network programming draft, if it goes through unchanged, then we'll just push ours through too. If there's changes, then of course we have to adjust. Anyway, the main point is, like, let's not become a part of the appeal process, right? So we'll just wait for that to play out. That's about my take on that.
Yeah, I'm in agreement that we've got a lot of important things that are at a technical level that we need to discuss. We really don't want to waste any working group energy on or mailing list bandwidth on debating this one until it settles down a little bit at least in the appeal process.
Joel agreed on Jabber saying it sounds eminently sensible to stay away from the appeal mess.
Okay. Okay, this one I think Engine has asked for a working group last call. I guess I'm a co-author on this. I think it's almost ready. There hasn't been any pressing need, but I think it's pretty much ready. So we'll take that to the list. And then we have these ones. These are really working group documents. I haven't asked. I think a lot of the first two people have implemented it. I think just it's a matter of getting good reviewers and working group class. I think they're ready. And Yang models, we haven't really been in a hurry with those. I put the ones. I definitely put the dynamic flooding and flex algorithm ahead of those just because there's implementations proceeding. And we covered, the extended hierarchy and in the last session. There's no pressing need now. Nobody's talking about implementing that. So I think we probably downplay whether or not when we want to do this. Yang models for additional features, extended LSAs. Yeah, we could do those. All these Yang model ones, it's just a matter of, getting all the reviews and doing them. This one, I think we're kind of dropping. Doesn't seem to be a lot of interest in it, the routing for spine leaf topology. Mainly because I think the main reason is because the other flooding optimizations are more generalized, and this was really just specific to the data center spine leaf between those type nodes. So if nobody's going to implement this one and it's expired, installed, we're not going to, it won't be on the status anymore. Mode for, I don't see any others I need to talk about. Okay, we've got this one. This one's on my list to kind of review and see if it's ready for adoption. The other ones aren't a high priority. Okay. The other thing I was going to say regarding the interims, Chris and I were talking about maybe having an interim also, like this one's subject on the flooding, maybe have one on the area abstraction and flooding reflectors, just on that one topic before Madrid. There's no reason, since we're going to be it's almost in certainty we're going to be doing interims anyway. So maybe get some discussion, keep the energy going on those. Thanks. That's it.
Okay, I don't see anybody in the chat room on the mic line, so we didn't offend anyone.
Yeah, I just gotta. Too many. Where is the one I'm looking for?
We have a just filled
I
with
must
empty
have it.
radio space. Go ahead.
I must have this.
It's blank now, but I assume that's because you were just sharing the one application.
Yeah. Okay. Here, I found it. It was. I don't know why.
I think we should suggest to IESG we should have a postmortem.
Yeah. Why?
Get all the chairs together and talk about what worked and what didn't. I can see the application now.
You can see it now. I'm gonna try the slideshow this time.
Works good.
Bruno, you tell me when next slide, okay?
Okay, thank you. So this is Bruno from Orange. This is an update of.
Wait, I don't know why it's Don't tell me. I don't know why my preview did that.
You have to speak faster, Bruno.
Let's see if it, okay, it's not doing anything good.
It's an update of the draft that we had presented in Montreal about a year ago now, in July last year. And at the time, we had a lot of discussion during the two meetings. And we had also a lot of discussion on the mailing list. So it's about time to do the update. So next, please. So coming back on the problem statement, because it was discussed a lot in Montreal. So we are talking about link state IGP, which are running distributed SPF. And this requires that all the nodes have the same link state database. And flooding is done between two adjacent nodes. So we need to sync the LSDB. We need to sync the LSDB between the adjacent two nodes. And the faster, the better, because the duration of this flooding is equal to the duration of inconsistency in LSDB. I think or thought we had reached consensus on this, because at that time in July, we had a lot of discussion about whether flooding parameters need to be done at the same rate network-wide or not. So I'm assuming we are in line with that. Next. So there are two main use cases to flood relatively fast. The first one is node failure. So when you have a node failure, each of your neighbor advertises the failure of the link toward you. So depending on the topology of your network, so at least for Orange, it could be between 2 to 50 LSPs to flood because of a single node failure. For us, it would be good to flood in less than 100 milliseconds for fast convergence. And ideally 0 milliseconds for two LSPs in order to quickly do IGP convergence in terms of PE, because usually PE are dual connected to the backbone. So they have two adjacencies, so two LSP. The second use case is partition repair or restart of the node. Here you have much more LSPs to flood. So for example, somewhere between 1,000 and 5,000, whatever the number. And the duration is, well, whatever your requirement, but let's say a few seconds. Next slide, please. So, there were requests to have some data on the behaviors. So we did a lot of lab testing in lab to have an idea of existing behavior. So we use idealistic test conditions. So it couldn't be better. So we use a major implementation. So it's carrier grade. We use a high-end router. We use the same implementation on both the sender and the receiver. So there is no interrupt issue, no interwork issue, no difference of assumptions. So the same behavior on the sender and receiver. Next, only ISIS is running on the router, so no BGP doing interference. The link is within the lab, so it's 0 millisecond RTT. And we have a single IGP adjacency. So there is a single receiver, there is a single speaker to sending LSPs to the receiver. So it couldn't be better in terms of condition. Next slide, please. So I'm not going to go into all details, but just a summary. So three kind of tests. One with default parameters. In this case, we have somewhat slow LSDB synchronization. No surprise, it's as per user manual. Everything works fine, except it's not very fast. It's about communication is below 500 kilobits per second. So in order to flood 4,000 LSPs, for example, you need 150 seconds. But other than that, it works fine. Second group of tests, it's trying to tune the parameters. So when we had good parameters, we had a good LSDB synchronization, much faster. It's 30 times faster. Still, it's nothing to be extremely proud of. So my smartphone could do better in terms of bandwidth, including over Wi-Fi and over the internet. So for the same use case, for the same test bed, we have 5 seconds to flew that. So it's much faster than 150 seconds. And again, everything runs smoothly. And then the third group is if you try to go a bit beyond the best parameters. So you have a little bit too aggressive parameters. So in this case, by definition, the receiver is overwhelmed. So you cannot handle all the LSP. Even in those best conditions, so you have only one speaker, it's a big router. And as a consequence, you have a lower output. So it takes 3 times longer, so 15 seconds. You have obviously higher load on both nodes, and the sender needs to send some LSPs multiple times.
I just want to point out that in Europe, for some people who might be confused, there's a comma rather than a point, than a period.
Yes, sorry.
Between
Yes.
the fractional point and the
Yes, good point.
non-fractional.
Thank you,
Yeah.
Yes, thank you, Essie. It's a comma at some people are used to a point. So for example, for this case, the duration is 5 seconds. 15 seconds, sorry. 15.112 milliseconds. So it's much slower, 3 times slower, even though the parameters are slightly different than the tuned parameters. So this is caused by a lack of flow control because the sender is not listening to the condition of the receiver.
Bruno, I have a question. I don't know if this is in the, I just read the draft too, and I can't remember if this was in there, but
No, it's not.
knowing the, yeah, so knowing the parameters you use would be interesting here. And also, yeah, that would be interesting. So to know like how much overwhelmed, like does it, if you change the parameters, so you overwhelmed it, but you know, if you overwhelm it 2 times that or 3 times that or 4 times that, how does that change? You know, do we stay at sort of a steady state of 15 seconds? Or does, you know, does sending it faster, you know, faster, you know, change the convergence? Or,
It's a valid question. If I answer that question, I will probably need to disclose the name of the implementation. So I'm not sure about. But it's a small change, and you can see that in average, the inter LSP delay, which is sometimes called LSP pacing delay. For the tune parameter, it's 1 millisecond. It's not my mouse. It's 1 milliseconds 0.2. And for the 2 aggressive parameters, it's 2 milliseconds 0.4. So it's 2 times. It's not exactly the difference in terms of parameters, but if I go into more details.
yeah. So I mean, I guess what I'm saying is if they're disassociated, right? Like, so if you went from 1 to 2 and you know, then run it again with it at 4 and 8, and you know, do you see 15 go to 30, go to 60, or do you see it stay at about 15? That'd be interesting sort of insight into how you know, the standardized IS recovery works.
With a single sender, I'm about reaching the full capacity of the sender. So I can't really go much beyond. But we could use 2 sender because it's a typical use case. For example, any PE have 2 adjacent neighbors. So with 2 neighbors, we would multiply the load by 2. That's something that we can do, but then we have some synchronization issue because well, you want both to send at the same time.
Yeah,
It's-
okay, well, we can talk about it offline. I'm just
Okay.
curious, you know, what, if there was if they were dependent on each other. Thanks.
So next. So that's all for the test, just a summary.
Yeah, that is really interesting, that if you have somebody who just goes with a naive assumption that faster is better, they're actually going to go 3 times slower.
Yes, absolutely. Just because you're overloading a bit too much your receiver, and then you have a set of LSPs which are lost or not acknowledged fast enough. So the sender needs to send again. So it has loads on the sender and receiver. It's not a linear reaction. So what's the problem? It's a transport layer discussion, so it's not very new. There is lots of work on that for decades. So we could typically use TCP as an example. What we have in the toolbox is flow control, congestion control, and loss detection and recovery. And we look at those three. The next slide. So next, please. So flow control. So what's the goal of flow control? It's to prevent the sender from overwhelming the receiver, unless we're trying to avoid losses and retransmission, because the sender was too fast for the receiver. That's the definition of flow control. So it's end-to-end between sender and receiver. And for that, TCP uses a receive window, which is advertised from the receiver to the sender. And the draft proposed to use exactly the same mechanism, except the unit would be in a number of LSPs, whereas LSP use a number of bytes, because ISS and LSPs, whereas TCP sends a stream of bytes, so the unit is different. So next, please. Next slide, please. So we advertise the receive window, so there has been a discussion about what value we want to advertise, and how hard is it to find that value. So there are multiple solutions, starting with the easiest one. We can advertise a static value, so never changing. And even with that static value, we achieve dynamic flow control, thanks to having dynamic acknowledgement of LSPs using a regular ISIS mechanism. We do have a well-known limitation regarding bandwidth delay on Windows. There is a relation. So if you have a fixed window, the higher the delay between nodes. It's not only the link delay, it's the feedback delay. So it's between applications. It includes the reaction from ISIS. So the higher the delay, the lower the throughput. Otherwise, you need a larger window. So nothing new, a typical trade-off. So for a given size of windows, there is a benefit in sending SNPs faster. I mean, acknowledging LSPs faster, because you can have a faster feedback loop and you have a faster throughput. Still, there is a question of what value to pick. So typical answer is whatever you want. So for example, it could be just like TCP. So if you have TCP on your device, somehow TCP advertise a receive window. So you can use the same value. Another option is to use a platform dependent value. So you would use a different value for high-end node versus a low-end node. Because obviously the drawback is that use the same ISIS implementation, you bring a platform dependent consideration. But you can also advertise a platform independent value, just like it is done today. This is clearly the worst case, but it still works. We still have flow control, and we, even with a relatively small window, we can try to have a good throughput by sending SMP faster. It really depends on the speed of the feedback loop. So what short answer, you can pick a static value, whatever you want. For some implementation, they already send multiple LSPs back to back, for example 5, and you can reuse that exact same value because it's a receive window. Next slide, please. There is another option, a bit more dynamic. You can change the window, receive window, based on the receiver load, so your load. So you can increase the window if you have plenty of resources. So basically, you're waiting for I/O. You can receive more LSPs. So you're waiting for more LSPs. In this case, you can increase the window, which is a way to send to your sender. Please go ahead and send more. On the opposite, if you cannot eat or consume all your LSPs, you can decrease your window, which is a way to signal to the sender that it's speaking a bit too fast to reduce the load. So it's a relative message, faster or slower, please. Next one. And there is a third solution. It's to advertise a dynamic window based on monitoring some relevant resources within your platform, within the receiver platform. So typically hardware resources, such as buffer space or CPU or whatever. Clearly, in this case, it's hardware and platform dependent because you are monitoring the hardware or software resource, which are the limiting factor for your implementation. So that one is hardware dependent, but again, it doesn't have to be that way. If you want to do that you can. If you don't want, you can simply advertise a static value. For example, the same that you have today, 5, or pick your TCP window and advertise the same value. Next one, please. So second tool.
Can I ask a question? This is a naive question, perhaps. Be studied on the on this stuff, and I haven't been deep inside TCP. Does TCP, you mentioned that the receiver advertises the window size. Does it do anything with dynamic adjustment of the receiver window size?
It's not so naive, and I'm not an expert in TCP. I can try an answer. As far as I know, you can increase the receive window, but it's thrown apart to reduce the receive window because you can block the communication.
So, but there are implementations of TCP that try to dynamically size it with the connection. I'm just trying to decide if did transport take this on, or do they just go with, static picked, I know it's adjustable, but is it dynamically adjustable?
I don't know implementations well enough. I would assume you know better than me. But from the protocol standpoint, you can change, but you're not supposed to reduce it.
Okay. Thanks.
So next slide, please. So the second tool is congestion controller. So here the definition is to prevent the sender from overwhelming the network. So the network is between the nodes or between the applications. Here the application is ISIS. So for ISIS, we have a specific case. The network is not that big. It's mainly one point-to-point link, which is very high speed. I think we agreed that it's not going to be the issue. But if you go a bit closer, There are also some forwarding resources within the router between the ingress link and the control plane. So it could be the matrix or some links between control plane and switch matrix, or between ingress and between CPU and the LAN card and some control plane. So clearly it's platform dependent. And we don't want to, or maybe we don't want to look at the details. And we'll just assume it's part of the network between the two applications. So we don't care about the details. We don't need to look at that. Because over the internet, there is no assumptions about knowing the topology of the network and the resource. So next slide, please. So on that, maybe Chris will not agree, but I'm not sure we need a standardization, especially if it's just for ISS, which is a high priority. That's why it was not in the current version of the draft. However, we can add a congestion control, and we probably will in the draft, at least to prove that it's doable. And we're not going to invent anything new. So we'll just reuse the existing AIMP algorithm, which is additive increase, multiplicative decrease, which is the one which is very old, nothing fancy. And it's used in TCP, SCTP, and some DCCP modes. So it's quite simple. You start with a congestion window, so it's kind of slow start. You don't want to start too slow because it's not effective for short duration of message. So one option is to start with half of the receive window, whatever. But one is too small. It's too slow. And then you do a linear increase if everything goes well. And we can do a proportional control. So if you have received correctly n LSPs, you can increase the congestion window by n. And in case of bad cases, so you have LSP lost, you do exponential reduction. Typically, you divide the window by 2, or whatever value, but let's use the same value than TCP. So again, nothing new. This is the one from TCP. Next, please. And then finally, for the transmission layer, we have LSP loss and retransmission. We have already existing mechanism in ISIS. But still, having a faster loss detection would improve the feedback loop delay. For congestion control, you need to detect loss. The faster you detect loss, the faster you can react. And currently, ISIS ISO-spec assume at least 5 seconds, let's say between 5 and 10 seconds before retransmitting LSP, sorry. And what the draft is proposing is that that value could be advertised by the sender, hopefully advertising a smaller value. And if you advertise a smaller value, you say you commit to send faster acknowledgement than the value that you have sent. So for example, if you say 2 seconds, you commit to acknowledge the LSP before 2 seconds. And with that, you can detect LSP faster because you have a commitment to acknowledge LSP before 2 seconds. So if you have no acknowledgement in 2 seconds, it's a loss of LSPs, 1, 2, or 3. And if you're very smart, you can change that value. So if you have nothing to do, you can commit to acknowledge fast, very fast. If you're quite busy, you say maybe I will be less optimistic and commit in 3 seconds. Wow, jump in already.
That's what I thought.
Next slide, please. So in summary, we can summarize everything in just one slide. So the draft proposed to reuse a TCP-like algorithm. So for flow control, advertise a receive window. And so just like TCP, we allow for a small value of traffic if the window is blocked. And for congestion control, we use the additive increase, multiplicative decrease congestion control. So everything is a copy of TCP, no invention. And for advertising the value, we use ISIS behaviors on encoding. So for ACK, it's the regular behaviors for ISIS. Same thing for loss detection on retransmission, same behavior. And we do need to advertise a few values. So for that, we advertise a TLV with some parameters. So the receive window, the amount of small traffic allowed if the window is full, and how fast I will hack LSPs. Just discuss that. So all is optional. Next, please. So that's a summary of transmission layer. In terms of going into a bit into more details, the draft, the change in the draft since Montreal, following some comments, we are allowing the TLV to be advertised both in LOs and SNPs. Again, following some comments during the meeting, we will use sub-TLVs, one for each parameter, for extendability only. We use 30 bits value for future proof and increased granularity. We have also added two sections, one related to faster acknowledgement of LSPs. And you've touched that in the slide, sorry. And one related to faster retransmission of lost LSP, which is faster loss detection of lost LSPs. Again, we've discussed that. We already discussed that we need a new sub-TLV, a new value. So we change the terminology and do editorial stuff. Change, I mean improvement, I guess. Next. So we already received a lot of feedback, especially in Montreal, during the meeting on the list and private conversation or private email. So thank you. We could improve the draft. Always welcome. Next step is to update the draft, which what we have presented today. A better introduction regarding the transmission layer and what we are doing at the overall behavior before deep diving into TLVs, and adding the congestion control algorithm. And thank you.
Okay.
So this is Chris Hops, speaking as working group member. I watching the slides, it became obvious that this is a very what do you call it? It's doing a lot. There's you're talking about flow control. You're also talking about congestion control, and then we're also talking at that last slide. AC, if you put it on 15, well, it's up there anyway. It says new sections, right? So that's even a third aspect, right, which is modifying the protocol mechanisms.
The values mostly.
Yeah, no, I mean, I'm not none of these comments are objecting to any of this.
No, just a precision.
Yeah.
So,
Yeah, so that's cool. What I would, I think I have a different idea of flow control and congestion control. I'm not necessarily right here, but I tend to think of when you say congestion controls on the network, I think really congestion control is about managing loss. That's how I think about it. So the loss sure can happen in the network, but it can also happen in the router, right? And I think
yes.
we've talked about that on the list and stuff where people have talked about different queues and loss points. So I think when you're solving the problem of loss, that's really when you're talking about congestion.
I agree. Yep.
So, and something I wanted to bring up that I don't think we've talked too much about. I see flow control, at least the basic form of it, if we go way, way back to RS-232, right? Um, you have flow control as a way of saying, stop sending, right? Um, and it's less about congestion control algorithms work off of data like loss rates, whereas in flow control is more I see it as a more active, and I think that we should also explore this. I don't know if it will pan out, if it will be fruitful, but just throwing out there a simple sort of idea, you could, you know, look at your first level queue, and as long as your routers, your NPs or whatever are doing, depositing things, ISIS in its own queue, you can tell the other side to stop sending. I know there's a lot of multiple queues and all that we've discussed before, but queues drain, so you can tell when the first level queue is not empty. Anyway, the point is, I think that we should also explore that idea because it could be a very simple solution. So I sort of have dropped that into the flow control category and then put everything else in the congestion control category. So for that, from that viewpoint, the receive window, the dynamic receive window sizing, kind of what you're talking about in the draft, where you're sort of advertising, hey, use these retransmission timers and these, pacing intervals. The way that sort of I perceive that is a sort of second order modification, a second order input to the congestion control, or almost modifying the congestion control algorithm. Right. So at the first order, input to a congestion control algorithm is your loss. Your round trip time, generally it's like round trip time and your loss rate. Uh, and those variables, they're not hard to, they're there already in a limited sense from your NAC-ACK. And then, so what I think you're proposing is sort of like above that, and it's like going in and saying, I'm going to modify the behavior of the congestion control algorithm. So that's an interesting take. I wonder if we're biting off more than we need to there, but it's definitely worth investigating. Yeah. So that was my main comments on what I was thinking. Let's check out like the Ethernet pause CTS RTS and see if that simple thing might work. And let's the receive window stuff seems complex since it's more modifying the congestion control than it is just giving input to it.
It could, so maybe I was not very clear, but it could be simple. You have many well, at least two implementations. So again, no names, which allow to send multiple LSPs back to back. So let's say 5. It mostly means that you assume that the receive window is 5. So it's already available on some implementation, except that this is a sender who is trying to guess what the receive window is, whereas it's a resource on the receiver. So you can pick exactly the same value that you have today, so 5. And it's not complex to advertise 5, at least in my opinion.
Well, so I'm not sure. I think you're talking about the burst rate, right?
Yes, receive window.
So the burst rate is not actually like a receive window because you still have to pay attention to the limits. So it's more like a buffer size, right? I mean, maybe that's what a receive window is, but it if you send 5 back to back, but you only can send 5 per second, on average, you still only send 5 per second. It's not going to go, nothing is going to go faster. It just lets you send the 5 immediately. So it won't help speed things up is I guess what I'm saying, which is really what we want to do, I think.
Yes, the goal is to say you can send 5 back to back.
Right.
And
Once we start talking about you can send 5 back, you can send 5 up to 5 unacknowledged, right? But then you don't put any more limits on it. That's when you start speeding up. But the current
yes, that's a proposal.
Yeah. But I'm just saying, I think that's different than what's out there implemented, right? What's out there implemented will send 5 back to back, but then wait a whole second before it sends another 5, acknowledged or not.
Should we do the other less and then have a general discussion?
Yeah, I was hoping my comments were just focused on that one draft.
Yeah.
I
don't know if is anybody else in the queue? That's what I'm wondering.
Nobody's on the queue. I was hoping we'd get lots of cool engineering design talks, but yeah, maybe everyone's waiting till the end.
I did have my hand up.
Oh, we can't. I've shrunk participants so I could see the chat window. Sorry. Throw a Q in the thing next time and I'll see you. But go ahead.
Hi, this is Tony. One thing I wanted to point out is that we've been very flexible in this draft. We're not trying to say that all of these knobs are necessarily useful. Certainly don't know what the right answers for setting them are, but the point is to allow massive experimentation. What can we do to optimize performance with minimal changes to the protocol? And so this is just giving people lots of knobs to play with. I really would like to see people go off and play with the knobs and see what happens.
Okay. Yeah, that's a valid point. Let's go through his and then we'll have a general discussion on the two. Are you ready?
1 second, AC. Do we have Ying Zhen online?
What?
Is Ying Zhen on?
I've got my
I just didn't notice anything in Etherpad, so I guess I'm gonna try to take minutes too.
I know, I think she's doing it in her own.
Oh, okay.
Okay.
Les?
Yep. Next slide. Okay. Yep. Next slide. Yeah. Okay. So this is start with a quick summary of the changes since E1. Next slide. So we put in a new example flow control algorithm. Note here, of course, that this algorithm is based solely on input local to the transmitter. So that's the big point of difference, I think, between the two drafts. I'm not going to spend a lot of time on the details of the algorithm itself. We do think this algorithm reacts quickly than the first proposal. But the algorithm itself is not intended to be normative. It's just an example. And we think it's quite possible for people to implement different algorithms, and they're still going to be interoperable because this is a local matter. Again, the key point here is that the input to the algorithm, other than the configured values, is the current number of LSPs that have been sent to a particular neighbor, but for which we have not yet received acknowledgement. And this is information that's already known to the protocol. Next slide. Sending PSNPs, which is on a point-to-point circuit, which is the way LSPs are act. The base protocol specifies a relatively large timer of 2 seconds. If we're going to do faster flooding, then clearly we're going to need to send acknowledgements faster. I think implementations today don't necessarily adhere to the 2-second value, but they kind of stay in the same range. They might be 1 second or a little less than 1 second, but they're certainly not much faster than that. And we think that needs to be changed. I think this is something that Bruno talked about as well. So we're in agreement on this point. Next slide. There was a comment on the list, I think from Robert, about what happens when you get some nodes that are flooding much faster than we do today and other nodes that do not yet support this. This can lead to longer periods of inconsistency in the LSP base in various portions of the network. So we added a section to recommend that the faster flooding not be enabled until all nodes support it. Flooding is scoped by the area, so you could enable this in a particular area if all the nodes support it, while the nodes in another area or in the L2 backbone don't yet support it. So that's possible. Next slide. Okay, so those were briefly the changes to the draft. The bulk of the presentation now is going to talk about discussion points, and I think particularly trying to focus on those issues which are different between the two drafts and for which we have yet to reach agreement. Tony, I apologize for appropriating your phrase of optimized goodput without permission, but I think this is something that philosophically we all agree upon. This is our goal. What we differ on is what we think the best way to achieve that is. So the following slides will go through a number of issues. Let's go to the next slide. So a receiver-based flow control algorithm needs to get input from somewhere. This is in other words, you send LSPs, but what's the state of what happened to these LSPs on the receiver? Did they get dropped? Are they in queued? Are they in queued in ISIS itself or down in some of the queues from the data plane to the control plane? And we took a look at least existing implementations of platforms as to what kind of QoS they apply to ISIS PDUs. The operation of different data planes varies a considerable amount, but I think it's generally true that most platforms do not implement a QoS specific to ISIS PDUs. They lump ISIS PDUs either with all incoming traffic that needs to be punted or some subset of that traffic, which could be all the routing protocols, BGP and BFD and so forth. There are varying ways of doing this. They certainly do not typically apply QoS specific to ISIS PDU types. So what happens to the fate of LSPs as they're being punted from the data plane to the control plane is shared by hellos, for example. So it's pretty challenging for the control plane to get the current state of all of the incoming ISIS PDUs. How many of them are in queued? Where are they in queued? How many of them get dropped? Is this specific to a particular interface? Because in most implementations, the statistics that they use to control the punting is not based on a particular interface, but is lumped on all of the incoming PDUs across all the interfaces. Second point is, in order for the flow control algorithm, receiver-based flow control algorithm in ISIS to operate, it's going to have to get updates from the data plane as to its state in real time at a fairly fast rate. If you only communicate this information, every 30 seconds or every 10 seconds, you're not going to be able to respond quickly to the current state of flooding. Given that,
Go ahead. I'm sorry. I have a question on this slide though when you're done.
given that we have a variety of implementations, even if when we try to define some sort of platform-independent API as to how to send state from the data plane to the control plane, it's going to be difficult to try to map the platform-specific behaviors into a common notification to the protocol. So we see these as significant challenges to utilizing a receiver-based flow control. And if one of the goals is to try to get faster flooding deployed in a modest amount of time, not many years from now, and to not impose restrictions on how new platforms need to handle the QoS for ISIS PDUs, this is something we see as a huge barrier to implementation. Alternatively, if you use a transmit-based flow control, as we proposed in the draft, all of the input to the flow control algorithm is local to ISIS and is in fact information that the protocol already has today. And that data is per interface, because the implementation of the update process in ISIS requires us to maintain statistics on what LSPs need to be sent on a per interface basis and whether they have been acknowledged or not. Chris, did you want to?
Yeah. So I'm sort of curious on what you put out a range of things that are possible or not, maybe not possible with hardware that's out there. I mean, I think any ISIS is generally deployed in higher end routers. So I would be shocked to find out that any successful router didn't separate ISIS traffic at least from data plane traffic. Other than just punting all control traffic. I mean, but yeah, go ahead.
So are you sitting down?
Yeah. Yeah.
Okay, so be shocked, because I have talked to some of our implementations, and in some cases, not all, but in some cases, that in fact is the case.
Okay.
They do not distinguish ISIS PDUs from the general 4S traffic. The limits that they impose go across all packet types.
So yeah, I guess my bigger
That's
comment.
that's not to say that every implementation does that, but there are certainly some that do.
Right. And so that'll lead into my next comment. By the way, this is a working group member. These might be barriers, but as an old DepBSD guy, I'm familiar with trying to implement things on ancient hardware or bad, whatever. That doesn't mean we have to engineer to it, right? So, for example, we could say, I mean, this is not hard to do, right? Whether it's done widely or not is one thing, but it's really, for example, ISIS sort of almost always gets separated very earlier in the MPU stage because it's coming in on ISO, right? So it's like it's usually noticed at the very first thing that it's not a normal Ethernet packet. So it generally goes into a different queue. Maybe not always, but my point being, it's not hard to do. It's not hard to recognize ISIS packets outside of other packets. And so what I'm basically getting at here is let's not throw out a solution just because we have to engineer to it, right? Because if we had a simple pause solution, we could present that as something the market could decide on, right? So you say, okay, well, our implementation of ISIS allows 50 millisecond convergence across the network because you're able to, flood so quickly. And our flow control is so efficient because we did this little tweaking on our line card in the MPU, right? And then you have the market deciding. So I just don't want to throw out possible solutions because current hardware might not support it. It is a barrier to implementation, but hey, the market can decide and people can make money on providing good things. Right? That's my only comment on this.
So here's maybe an input from practical implementation of all the stuff. The transmitter is very useful, works actually pretty well. The receiver, you need very high frequency for the stuff to work well, which we simply don't have, right? So you have to start to go towards things like TCP that does 200 millisec and RTT estimates and so on. So you get yourself very quickly into designing a completely new transport, and that's a mild rat hole. Also, if you start to run on such fast timers, you basically have practical problems in terms of ISI's implementation. To prevent slips, you have reordering of packets, you have a lot of queues and so on. So my experience is that you cannot get a decent feedback even at 500 milli. And if you get 500 milli to start to flood real fast, mostly your burst is already gone by the time you can do something. So, I mean, if you put the stuff in, because in the future, whatever may fly with big enough engines, that's fine. But sliding into designing a new transport is probably not the best of ideas. Also because pretty soon you end up again into the BGP problem of collisions, right? So you start to build a session layer. Just my practical input from having done the stuff.
So what do you say to my idea that I have an ISIS queue at the line card at the simplest state? If it isn't draining, it's full, and I send a pause.
Right, so you start to generate ISIS packets of the line cards right at the very bottom, something
Just
special.
The pause. Just the pause. I say the queue's full, I can't put any more in, I'm going to pause.
But you have to put it into something, right? And now you have a system that starts to emit packets somewhere at the very bottom of the line card. To debug such systems, or even operationally try to figure out what's going on, can be pretty challenging. But yeah, it's an idea. But what you put it in, so you start to generate, like hellos. Those are practical things.
Just have an ISIS queue on the line card, and if it's 80% full, you send a pause back. That's it.
Yeah, but what is pause? You have to put it into something. So now you start
Protocol thing. Yeah, that's the thing I'm saying. We would definitely have to have a packet that we sent back to the sender saying pause.
Your line card starts to generate packets all of a sudden that the implementation knows nothing about. Or you have to implement it the way that the line card starts to report it back to the main implementation. Those are not easy things to build. And again, depending on the timing, your mileage will vary very much. It all boils down on the fact whether you can implement very high resolution timers very precisely. And we all know the user space, this is pretty much a proposition from hell at scale.
I see the timer thing though. If I'm sending a pause, it's either listened to or it's not listened to, right? But I mean, I don't see a timer.
So Chris, the comment I would make is that your proposal only takes into account one point in the chain of punting from the data plane to the control plane. Yes. There are other points of congestion. So even if we were to agree, and I agree with what Tony has said in terms of the implementation problems of this, but even if we were to agree that, okay, let's do what you suggest, it does not cover all of the points where the PDUs may be dropped inside the box.
It does happen. It does. If you're not dropping them, you're just you're not draining the queue, right? Then you get the pause, and the control plane drains the queue. Anyway, I'm saying all I'm saying, because I know there's some contention on this, so I don't want to hold this up too much.
I'll give you an interesting implementation input here. So Rift has something like that. But for the stuff to work well, it's actually far more useful in a different context. And we cannot do it in ISIS because everything is meshed together into the same LSP. if you can, like OSPF, differentiate prefixes from node description, that it is highly beneficial to actually push on the sender saying, look, I'm having trouble processing. Please send me only node description. In terms of deployment, this is actually quite.
I mean, why can't, as long as the MPU can say this is an LSP, and I've got too many of those in my queue, right? It's not a lot of logic, and it can easily generate a pause from that. Now, whether the control plane, you know, and how to deal with that, I don't know. I'm just saying, I don't know. I don't want to throw this out so quickly. It might be an add-on solution. It doesn't have to be the solution, but I don't think it, you know. And I've done a few implementations and worked on some of this hardware. I'm not convinced that it's that hard to put this in a simple thing into the line card network processor to do this. But you know, we can disagree too, or we can argue on the list as well.
No, it's a decent idea, possibly not easy to implement. If you really are willing to emit a packet very close, you know, the reception, and you have some idea, you know, what you're overrunning, yeah, it's something to think about. I agree.
All right. Next slide, please. AC, you still?
I went the wrong way.
Okay. One of the proposals mentioned in draft Ukraine is the possibility of using static controls to control the flooding of LSPs. Start to think about, I think, the part of the discussion that I think we've had a little bit on the list already has suggested that, well, you could do some offline testing of a variety of scenarios with, you know, your particular platform, and, you know, come up with a relatively modest number of values that could be used. But I think this is not consistent with, you know, the mantra of optimized goodput. If you start thinking about all of the things which can influence the LSP flooding rate and the behavior of the receiver, you know, these are just a partial list. You know, how many nodes do you have in the network? How many neighbors do, you know, does the node that is receiving have? What flooding optimizations be supported by the neighbors? What other protocols are enabled? You know, what's your link bandwidth speed? You know, obviously, what's the speed? What is your hardware capable of doing? What is your SLG deployment, which can influence the number of LSPs that might be triggered as a result of the topology change? You know, I'm sure there's many more that people could contribute here. So the idea that you could have a modest number of scenarios for a particular platform and say, okay, I'll pick scenario one and I'll use these values that I set based upon offline testing. I think in order to optimize goodput, you're going to have a very large number of cases that you test offline. So the idea of using static controls doesn't seem like it's consistent with getting optimal behavior. Next slide. So there's a lot of discussion about comparisons to TCP. TCP uses a receiver-based flow control mechanism. Why can't we do that for ISIS? I think the analogy between TCP session and ISIS flooding is far from perfect. Obviously, TCP is byte stream, ISIS is packet-based. Key to the TCP control is the fact that you have ordered delivery, meaning if I receive, you know, byte 90,000 in my data stream, that presumes that the sender has already sent me, all of the bytes up to byte 90,000. But in the case of ISIS, if I receive, LSP number 5 from node A, this tells me absolutely nothing about whether there are other LSPs that have been updated from node A, whether there are other LSPs that have been updated from other nodes. I can't infer anything based upon what I have received about what I may not have received. TCP is based upon a single independent data stream that have a connection from node A to node B somewhere else in the network. With ISIS, when I get an LSP update, this is going to trigger sending LSPs to all of my other neighbors, or perhaps a reduced set of neighbors if I'm using some sort of flooding optimization. So any event in the network is going to trigger flooding streams on multiple interfaces. The resources that are used for TCP and are used to trigger the adjustments to the window are managed by the control plane. We set aside a certain amount of buffer space for a particular session. In the case of ISIS, as we've been talking about, the resources for receiving ISIS packets are dependent on the data plane. We've got input queuing, we've got intermediate queuing going towards the control plane. We may have multiple levels of queuing in the control plane. So I don't find that to say what works for TCP, there's no reason that it shouldn't work for ISIS. I don't think that's a fair comparison, and it's certainly not intuitive to me. Next slide. Flooding characteristics. So these are just sort of the basic flooding scenarios. I think a lot of this Bruno also covered in his presentation. So if you have a stable topology, then during that time, the only thing that we're flooding are refreshes. These can be distributed if you're in a network that has a lot of LSPs. Then it's advantageous to use something other than the default lifetime for your LSPs. The default lifetime is 20 minutes, but you can, for most implementations, they allow configuration of up to 18 hours. It's a 16-bit value. So, the rate of flooding in a stable topology can be very slow. So flooding speed under those circumstances is not a concern. Then you can have a link topology change. This typically results in a small number of LSPs updated. Again, the draft talks about how to optimize LSP should I say minimize the number of LSPs that need to be generated when a single neighbor goes down. If you follow those guidelines, typically you're only going to have 2 LSPs that need to be flooded. If you have shared fate, you have SRLG, then a number of links may go down pretty much at the same time. This will have a multiplicative effect on the number of LSPs that need to be generated, but not necessarily linearly, because multiple neighbors are often advertised in the same LSP. So, maybe even with multiple neighbors going down, I still only have to generate 2 LSPs. But still, the point here is the number of LSPs that need to be flooded in these cases is also fairly modest. Then we have the node state changes. When you're bringing a node up, that node needs to get the complete LSP database. If the LSP database is large, which is the case we're really concerned about, this can take a significant amount of time. However, bringing a node up is not a time-critical operation, and there are techniques, which I'll refer to as graceful startup, that essentially allow this node to come up without being used for forwarding in the network until it's able to sync its LSP database. So certainly we don't want to do this as slow as we're doing it today, but it's also true that we don't need to do it as fast as possible. Node failure, however, that's probably the key case, because here the node was actively being used in the network. The node goes down. In order to get traffic reconverged, we need to handle all of the updates, get them flooded throughout the network. And if the node which failed has a large number of neighbors, then clearly we've got a large number of LSPs that need to be flooded. Maintenance mode is similar to a node failure, but here again, if you've got a smart implementation, you can mitigate this by graceful shutdown techniques. So the number of LSPs, the amount of time it takes to flood updated LSPs as the node goes out of service is not as critical. Next slide. So all of these considerations point us toward, what are our flooding speed goals? Currently, implementations are flooding on the order of tens of LSPs per second. 33 is a typical number. Other implementations may do something slightly faster, slightly slower. What is our goal? Certainly our goal, I think, is in hundreds of LSPs per second. We want an order of magnitude improvement. Whether we actually want to go to thousands of LSPs per second, I think is a bit aggressive and likely not needed, but it's a point that could be further discussed. The relevance of this is it helps us define what the adjustment interval that we need for flow control. By that I mean, if we're trying to flood a large number of LSPs per second, and we're only able to make adjustments to the flow control, say on a 10-second interval, because that's as fast as we can get the feedback as to the state, then this isn't going to be very effective, because by the time we make the adjustment, we've already flooded far more LSPs than can be handled, and then we're falling back to retransmissions, which we know are going to be very slow. Second goal, I do believe that to the extent possible, we want to keep the flooding rate interface independent. If you don't do this, then you're pretty much guaranteeing that some portions of the network are going to converge later than other portions of the network. Obviously, if you hit congestion, we're all agreeing that we need to do flow control. And so there may be cases where you can't avoid slowing down flooding in a particular direction. But I do think our overall goal, when the network is working well, is we want to be flooding at the same rate on all interfaces. Next slide.
Seems to be blocked.
So,
I didn't do it.
I have a quick, I mean, I'd like to explore, as a working group member, I'd like to explore this. I'm very confused by this whole thing about the same speed.
Sorry, by the way, AC, that's the last slide. Sorry.
Oh, okay. Yeah, so that I was going to say, oh man, do we have the wrong copy? Okay.
Sorry.
Yeah, that's right.
Go ahead, Chris.
No, just I mean, when I think about it in the Gestalt, right? Like if I think if we had a goal of flooding optimally, then and without loss, if we just did it, optimally, then the network converges as fast as it can. I don't see why we should be so concerned about whether one interface is going faster than another. yeah, if one interface is going faster than the other, then the node adjacent on the faster interface is converging quicker too. But that doesn't impede anything. It's just if you're optimally flooding, you're optimally converged. I don't understand
Well,
why we keep talking about, like there's some scary thing here. Like maybe we need to point out the scary thing more. I don't.
I think the point I'm just trying to make here is I don't think we want to be setting a goal of saying, well, on these interfaces on the left, because the receiver tells me that they can handle, much more than the guys on the right, that I want to be flooding faster to the left and slower to the right, because that means that for any event which occurs, even with a modest number of LSBs that are going to be updated, the left side of the network is going to converge a lot faster than the right side of the network.
So
I
what?
don't think that that's advantageous.
I mean, so we just slow the convert. I mean, let's talk about, there's good info and bad, like if we're talking about a network failure, we want to converge as fast as possible. Let's take a pathological, well, not pathological, but a simple case of you've got one really slow router. Why do I want that one really slow router to slow convergence in my entire network down? I'd rather route around that problem, right? And flood around it.
So what I'm trying to say is if you look at your network and you've got, one or two routers that are significantly slower than the other routers, this is a problem in the network, something that needs to be addressed. I think the analogy here is, what happened when we went from 5-second SPF intervals to 50 millisecond SPF intervals. Well, if you only did this on some nodes in the network, to some degree, you made the problem worse. That's all I'm saying.
I got a lot of noise. I think maybe Tony, I don't know if he muted. Yeah, okay. But I don't think this is, I think if you have a case where you're actively harming the network, that's worth pointing out. But I want my network to converge as fast as possible. And if I have a bad router, I want to know about it. I want to be alerted to that fact. But I don't want to slow network convergence down in the meantime.
I would agree with that.
This was the last. I'm going to let other people. Tony's got a queue. Go ahead, Tony. Tony Lee.
I thought John was first.
Oh,
Whoever.
oh, my chat
since-
window is one line now. I'm sorry. John.
Since Tony's not talking and I'm off mute, I'll go ahead and do my thing. I just had a follow up to Chris's comment, which is it's been too long since I've done this particular version of network Sudoku to know this for sure. But typically the answer to why is it a problem for part of my network to converge faster than the other part of my network, typically the answer is because you can form forwarding loops. Right. And so, I mean, I agree that like sometimes faster convergence is better, but the the trick is it's not always better, and sometimes it's not obvious. So I'm not really persuaded by either side of the argument here without further analysis.
So John, to speak to that particularly, we actually went through this exercise with ISIS a while back where we talked about good information and bad information, I think. And right, so in a perfect world, you want you want breaking things. If your network's broken, you want that as fast as possible everywhere because you're black holing traffic anyway, right? Whereas when you're making new, you're bringing an interface up that maybe is bringing up, just an alternate route. If you're introducing micro loops because of, convergence at different rates in different parts of your network, then that good information is bad to propagate at different rates. So yeah, there is a point there, but
the analysis has already been done. I don't want to try to redo it right now in the middle of the meeting, but black holing. If I'm black holing traffic, I'm consuming basically 1 times whatever that link was across the network. And if I'm forming a micro loop, I'm potentially consuming, something like 255 times what that link was in terms of bandwidth for some period of time.
Yeah, that's a good point. And I don't think we did, the analysis we did on this wasn't in, full, I don't think. So it's definitely worth reconsidering in this topic.
One comment maybe, if I can, specifically to John. So I agree with my groups, but you have my groups if you have but let's say LSDB inconsistency. And if you need to flood LSPs, because you have LSDB inconsistency, it's between you and your neighbor, but possibly in more nodes. So I don't think it helps to reduce the time it takes, the time you need to remove that inconsistency. I mean, it's not like origination of LSP. For that, I agree that you may not want to be fast. Once the LSP has been originated, someone has a different LSDB than the other one. And the only way to solve is to flood that LSPs to everyone, I think, as fast as possible. In all cases, you already have inconsistency.
So let me,
Tony.
Bruno, this is not. Sorry, this is not in Bruno. This is not in response to your comment so much as from the working group's perspective. My viewpoint is the big debate that we're having at the moment is, should we do a receiver side-based flow control or a transmit side-based flow control? And in the time remaining, this is just my viewpoint. I would like to see us talk mostly about that and not get lost in some of these issues, which may still be important, but are, shall we say, are less, are not really a point of conflict.
Tony.
I agree on just one comment. I think you're mixing flow control on congestion control, and what you're talking about is congestion protocol control, and I'm fine doing it TX standpoint, and that's also what we are proposing. But if you want to do flow control, I think it's end-to-end. The goal is to react before you lose LSP. That's the gain of doing flow control.
Okay, Bruno, you got to put a Q in the queue so you get in the mic line. Tony, you're up.
So my question to Les is very simple. Do you have any evidence to show us? Have you done any experimentation?
To show what?
To show that your solution does anything.
Well, okay, the easiest answer to that is actually the data that Bruno presented. I think reinforces the point. Okay.
No, it doesn't say anything about your algorithm.
Well,
It says that
Tony,
the state of the art sucks.
So, Tony, I want to keep this friendly, but I would like to point out we published an algorithm. You haven't. So
we're not trying to publish an algorithm. We're trying to set up some experimentation. How about we stop trying to decide without evidence? How about we sit down and write some code and put some evidence on the table?
And that's what I spent my time to some extent between this time and the last meeting, is investigating if we were to try to implement a receiver-based algorithm, what would we have to do? And when I go and
spending their time arguing, not coding. This is wrong.
Tony, in order for me to do what you suggest, I have to go to my platform teams and say, I need you to do this. We may have different opinions about what this is, but I definitely need changes from the platform side because I do not have the notifications that I need.
I'm not asking you to implement our implementation. I'm asking you to implement yours and show us that it performs.
That's fine. We can do that.
Please do.
Okay, for whatever it's worth. So the algorithm is basically a simplified version of what we're running in Rift. And the transmitter side has been very beneficial. And on the receiver side, Rift also provides basically a back pressure, something along the lines of what Chris is suggesting. And
Thank you for the pointless hand waving. Can we see some numbers?
so what numbers would you like to see, like the maximum speed you're going to achieve? That is, of course, very platform dependent. I can show you
Like
how
to
the stack
see-
is adopting.
I would like to see 2 implementations flood 10,000 LSPs. Okay.
Okay, so give me the other one. Maybe it's time to stop, talking and maybe implementing something.
I agree. That's what we're trying to do. Bruno puts up some numbers. That's a baseline.
Okay, I think that point is well made. Let's go to Peter.
Okay, just some observations here. So it looks to me both drafts try to do the flow control, and the flow control needs to be done by the sending side, right? It looks like the only difference is where do we get the parameters on, what is the buffer size or what is the amount of LSPs we can flood before, the number of LSPs, filled up and we need to stop. Whether this is going to be determined by the sender or the receiver. For the rest, it looks to me it's the same thing.
I agree.
Right. So all we
I
are
agree too, by the way.
all we are debating here, and to that point, if we are going to advertise the static values, well, I can say I can configure that on the sender as well. If we are going to do a platform static value, maybe then there is a value. If you are going to do a dynamic adjustment to the receiver window size, which, as I expressed many times, is very problematic in my opinion, that is a difference. But if we are talking static values, there's not much difference in what we are trying to do.
Okay, I'm in the queue next. So I have a sort of overall view of this. I think that maybe, okay, maybe I should say the goal first. As a working group member, I would like to see if we talked more about solutions. How do you put this? So it feels to me like when you're presenting this, we're getting a lot of data about why other solutions are not good, right? And I think that maybe that's not the best way to get things forward. Why don't we just talk about why your solution is good, right? And then, forget about saying these other, this one doesn't work, no, all the no nicks. And let's just get to here's my solution and it's really good and here's the proof of that, right? And I think that then, then we just get some good work out of this, right? I feel like we're spending a lot of time as a working group, in the mailing list and stuff, talking about, your solution isn't good because we can do it with mine. And I don't think that, I think we can get somewhere faster if we just say, here's my solution and here's how it works. Isn't it good?
So Chris, I think it's a misstatement, and it may be easy to fall into this trap. It's a misstatement. I'm not saying an RX-based solution is bad. I'm saying it's much more difficult to implement.
What I'm saying is, why are you talking about it at all? Why don't you just talk about the transmit solution that you've got and come up with some numbers and show and convince everyone that way why it's great? Because look at it. Look at the numbers. It works great.
If we could get
talking about what everybody else is doing.
If we could get 99% of the way there just from the transmitter, there's no reason not to.
Exactly.
Good. I agree.
I mean, the results should be basically the same if the static values are advertised. If the same algorithm is used on the transmit side.
Get numbers, right? I mean, we're just
but
guessing now.
No. But if you advertise a static value from the receiver, you plug it into your algorithm. What is the difference if you use the same algorithm and you use that values configured on the sender? There's no difference.
But again, why is this pertinent? Why don't we just talk about the transmit side solution and show how it works and get some numbers?
that's fine. And I guess what Bruno presented already proves that.
Peter,
We can then debate what is the right algorithm on the sender side to have the best results.
We can do that before we can just do that.
Yeah.
Why can't we just do that? Why do we have to say, Bruno, these statics, whatever, the average, none of that is pertinent. Just like say, here's we're going to go with the transmit solution and we come up with this great algorithm and here's how it performs. Like, I don't understand. I think that it gets in the way of moving forward to keep talking about why the other one is not useful or, you can just do it differently or, I mean.
As I said, there's very little difference between the two because I think
Peter?
Yeah.
So if we have to run around and configure different parameters on a per interface basis, even if it's static parameters, that's not going to make users very happy.
So I agree. I don't think, and that's the point that Les pointed out, we don't want this to be per interface. We want to behave the same in all the interfaces and be able to back off if the receiver, why not?
You've got interoperability problems. You've got different implementations. You've got highly capable control planes and less capable control planes.
So for less capable, I will slow down. I will slow down immediately, right?
How do you know to slow down? You don't have any feedback.
I have the number of ANACT LSPs.
Well, so that it means you do have feedback, and that means the faster implementations had to speed up what they're doing, which implies that we're changing protocol, which means we have to agree on that.
So Tony,
I don't see how we are changing the protocol here.
Yeah, we are not changing the protocol.
Yeah.
Okay. In our proposal, there are absolutely no changes to the protocol.
You are. You're changing behavior.
We may be changing behavior, but we're not changing the protocol. And there's nothing about what the transmitter may do that requires the code in the receiver to change. And
So,
if our algorithm, if the algorithm is sound, so that we are able to correctly and quickly adapt to the rate at which the receiver is able to process, then everything works fine. There is no interoperability issue. There are no protocol extensions required.
Who cares? I think we're getting hung up on that point, right? Like, okay, so whether you're changing the protocol behavior or changing on the wire behavior, I don't think that's pertinent to what we're talking about right now. I mean, it's not that hard to change the protocol either, right? We're trying to solve a problem, right? Let's come up with some solutions. Now, you could say my solution is really great because it doesn't change the on the wire behavior. Great. Right. But I mean, like getting hung up on like these, it's like splitting hairs and not getting the problem solved.
So again, a concern that we've raised, and we're talking here about, a dynamic algorithm, not a statically configured algorithm. Okay. If we are to agree that a dynamic algorithm, however driven, has a greater potential to optimize good put, in Tony's wonderful phrase, then doing so in a way that doesn't require significant changes to platform implementations as well as protocol extensions, to me is a plus.
Sure. So that could be a selling point, but I don't know why we'd argue about it. Like,
It's not my phrase, thank you, but that really belongs to VentSurf.
Yeah, okay, fair enough.
okay, we've been ignoring the queue for a while. Katan.
Hi, can you hear me? Okay. So I had a question and then a comment. The numbers that we saw from Bruno in his presentation, were they actually the numbers from an implementation that did this receiver-based dynamic flow control?
No.
So I'm just wondering, how does that in any way or results or data in any way prove or say that one mechanism is better than the other. In my view, it just describes what the problem and challenge is, and I thought we have an agreement that what we want to do here. It's just who does it, right?
Yes, that is a baseline. That is not a demonstration of any working code. That's simply to say that what's out there today, the default parameters are too poor. And if you turn the knobs randomly and just dial it up to 11, that doesn't help. And the right number, the optimal rate for sending, is not something that we know.
Right. So the burden of proof, Tony, would that also not fall for both the proposals?
Absolutely.
I want to back up
Okay.
to
Okay.
what something you asked before. I don't know if I agree. See, I don't view these two drafts as being in conflict, right? Because if I was implementing, I could do both, right? So I don't want to like let that go by if just as a working group member, but it's they both can be done. So there's no reason to like pit them against each other.
That's fine. I mean, I was just making the point because I got the impression that, for one of the approaches, we are asking for some numbers, but we don't have that for the other. So to be fair, I think we need data from both, right? That was
Agreed.
my comment. Yes.
Yes, we
And
need
the
data from
second,
both.
yes, and the second comment was that purely from a simplicity perspective, since it's a local behavior change, the second proposal that we saw seems something easy to implement or roll out, and also get deployed in a mixed environment without any interop issues, right? Whereas the other proposal has, we need something changed on the wire. So just my feedback, I think from that perspective, the second proposal seems, something easier or faster to get some
If it
benefits
works.
rolling. Yes.
If it
Yes,
works.
if it works. If it
So
works.
so yeah.
Second
So
one doesn't work, the first one doesn't work. I mean,
if the second one, yeah, that I think that's Tony's point is like, let's get some numbers, right? So yeah, not changing anything on the wire is preferable, but or at least it's a selling point, right? And we can like take all the data when we have it, look at the different outcomes and make decisions based on that. But I don't, to prefer an unproved solution because it doesn't change the protocol is sort of, vacuous.
I don't think that's the point that we're making. I think the point we're making is that in order for a receiver-based algorithm to work, it has some difficult requirements on the platform. That's the point we're trying to make.
Okay, well, that point has been made. So I don't know. I mean, we don't really, so it's going to require some work to do receiver side. But we've argued that point for like a long time on the mailing list now, right? Like, let's get down to, proving our own solutions or, checking them out and comparing them.
If that hard work is necessary, then we should do it. If that hard work is not necessary, then we should avoid it. There's no question about that.
I agree.
Okay, speaking as working group chair, then I think it would be good to further experimentation and data and even share results on internal algorithms. That would be my point. This discussion and possibly another meeting on this.
Hank has a message in the chat room that people might want to read. Les is replying to him, and Hank is replying to him. Hopefully that's captured in the. Maybe we could copy and paste that into the minutes or something.
I read it. I mean, I agree. It is not completely transmit because we are basing it based on what the receiver is acting, right? So, but this is just a terminology.
No, but that's like I love that's great. That's a great point though, right? Because once we start talking about solutions, And I sent an email earlier this morning saying, you know, we need to have there's a proposed algorithm, but it only covers point to point. So, I mean, at minimum, we have to at least cover point to point in LAN. And then once you have that, we can start saying, you know, does it work? And then once you have it does work, you can start like looking at, hey, it works even better if we modify the ACK and NAC behavior in ISIS, right? Not necessarily on the wire, but in the protocol, right? I mean, all those kind of things, but there's a progression that has to happen here, and it would, you know, be better if we just worked on that stuff. As a member. Hank apologizes, his headset wasn't working. We have Gang has a question.
Hi, this is Xuesong. My question is very simple because we seems are doing some comparison between these two solutions. My question is how, even if we can do some text, how can we do this? We can get a window size from the receiver side, and we can get another window size from the transmitter side. So whether we have an idle window size to judge which one is better, or we compare the convergence time or some other solutions to do this. For both of the orders, how to do the comparison, how to test which one is better, if we can do the test for both of them.
So Bruno showed a pretty simple, straightforward test. He's taking 5,000 LSPs and sending them from point to point. And I believe he was using TCP dump to look in the wire and watch for actual LSP retransmission. And you can see when the transmitter has done dumping the entire LSTB.
So if I get this right, we can see the retransmission times to judge whether it is better than another one.
That's one way. You could also take a snapshot on the sender of the sequence numbers, right? And then pull the thing. But I don't know if the control plane is fast enough. The management plane is going to give you the information fast enough. But yeah, I mean, basically, you have to test when all the LSPs have arrived at the receiver.
You don't actually have to test that hard because you can also watch the PSNPs coming back the other way.
Okay.
I'm not. Sorry, go ahead if you're not done, please.
Because I just want to try to figure out some parameters to see which one's better. For example, the retransmission times or some other parameters, and we can see it clearly which one is better by the numbers, right? But we have to know which numbers are these first.
So if you want, you can ask that on the mailing list too. Somebody will probably provide an answer to that, especially if you're willing to do the testing.
Maybe.
So I'm not arguing against.
Thank you.
I'm not arguing against doing testing, but let's not be naive here. It is not going to be so easy to compare the results from one implementation to another, because somebody will argue, well, you didn't do your receiver side signaling in the right way, or there's going to be many variables in here. Again, I'm not arguing against the investigation and the reporting, but let's not be naive enough to think, oh, yeah, we'll just have a couple of implementations and we'll compare and this guy will win. It's not going to be.
You can instrument the implementation. I mean, we're doing research here, right? So, I mean, I've got wrote like a Go ISIS or half an implementation for fun. I could just, literally load the thing with the expected result and have it signaling when it gets it. But anyway, are there more people in the queue? No, okay. Go ahead, Les. Sorry.
No, I made my point.
But you're right. We have to believe the results. It's like.
Yeah, and there's a lot of variables and wrinkles.
But actually, I think I have to say I kindly agree with Les. I think the answer may not be so straightforward. Because even in congestion control in the transport layer, we can just say one algorithm is more aggressive than the other one, or some other standard to judge which one is better. But maybe it is hard to get the answer which one is better, in my point of view.
Yeah, but I mean, ultimately, the result we're looking for is an LSP database with a specific, set of LSPs in it, right? So as long as you document that you've signaled that properly, there's not going to be a lot of contention about the result. It's not, it's a deterministic result. I've got LSPs on one side, and I need to know when they've gotten to the other side.
Yes, but maybe we can take it to the list.
Yeah. Okay.
I think it's hard to say how to do it properly.
Okay.
That's good. It's good to get some other people involved in the discussion too. I'm speaking as working group chair.
Especially interested in actually doing data collection. That's great.
Yes, exactly. Okay, I think there's definitely opportunities for, I mean, we're definitely going to keep this discussion going. I don't think we've ruled out or selected any work unequivocally today.
No, and I want to stress again, I don't personally, as a working group member, I don't see a conflict here, right? I think both of these solutions are not in conflict. We don't have to pick one, I don't think.
Concur, there is no conflict. There's just a lot of pointless arguing and not a lot of coding.
Awesome. Well, that would be a great outcome of this meeting, actually. If we stopped arguing and start coding. Cool. Anybody have any? I mean, I don't want to shut the meeting down because there's actually active chat going on right now. If anybody's
Move
looking
that to
at
the
the
list.
chat window.
Yeah.
Yeah, but if we lose the conversation, a lot of times we say, let's go to the list, and everyone goes back to their other work. Okay, anyway, I think
well, Chris, you started the thread when you were speaking as a working group member about there not being any active conflict. Please, everybody, please respond to that. We'll discuss that.
or just go off and do the proving.
Yes. Mm-hmm. Okay.
All right. Does anybody have any final comments? Otherwise, I think we're gonna end the meeting. Just speak up if you have any comments.
I'm hungry.
Okay. Time for lunch then, or wherever you are, but time to go to bed maybe.
I thought John was going to point out how much better the WebEx than we did in the IDR meeting, but I'm glad he's nice enough not to.
All right. Thanks, everybody.
Thanks.
See you on the mailing list.
Thanks, guys.
Bye.